Mm. So we're in chapter 11 of computer architecture, and we're hopefully going to finish today. We did example 1. Did we start? We started fully associative?
Yeah.
Yeah. We talked about it. We saw how it's you choose a random place. And we talked about two-way also. Yes?
Yeah.
Yeah, we talked about two-way.
I don't think we know. Yeah, we did do that slide. I think. I'm pretty sure.
Yeah,
I'm not
yeah.
sure.
We did this. We use the tag. We compare the tags of the two. Remember, we said it could be either here or here. We compare the tag of the two, and that tells us if one of them is true, then we have a hit. Yeah, we definitely talked about it. We talked about how this line is doubly connected over here. And that means that when this bit is lit, it doesn't matter if this is lit or not. This second one will come through.
0 and 1 is also doubly connected, though, right?
Well, no, maybe. That's what that line means. Yeah, I guess you're right. Just why
So
does he have it? You're right. There's a certain inconsistency.
2 to 1.
You're right. I take it back. You're right. This is also doubly connected. When I looked at it, it confuses me because he's got an arrow here. He doesn't have an arrow here. But you're right. And I thought this meant it's not connected to that line, but no, you're right. This is connected, but why are these lines here? Who can tell me why these lines here?
That's the what's that thing called? The block?
No, it's not the block. What is it? Why is there a line there? What does it indicate, first of all? In any diagram, what does that line mean? Have it over here.
That there's a bunch of lines.
There's a bunch of lines. That's what it means here. And now I can answer next question. Why are there a bunch of lines here?
It's the entire data. It's all the bits of the. Oh,
Excellent.
It's a byte. It's a full byte.
It's a full. Well, it's not given in this diagram actually. It's whatever the data is, whatever the size of the data is. I don't see a way of determining it here. Remember, the address can address a byte. It can also theoretically address a word. In MIPS, it addresses a byte. All right.
It looks like that mux is a waste. Shouldn't it be a 2-for-1?
No, because how would you do it?
It looks like it all depends on S0.
You have to have two. You have to have two. You have to know whether you don't. If you put, you have to have. You don't just want 1 or 0 here. You want to say that 0 indicates this one and 1 indicates this one. I don't know how else you would do it. What would you have?
It looks like S1 is the only thing that makes a difference. It doesn't look like S0 makes a difference.
You're saying once we know there's a hit, then all we have to do is see whether this one is lit or not. And if this one's lit, then it's here. And if it's not, then it must be the other one's lit. And give out the other one. That's what you're saying. We just need one entrance. Yeah, I think you're right. I think you are right. Yeah, am I saying what you're saying correctly?
Yeah, I guess so. I didn't view it like that conceptually, but yeah, I guess it makes more sense when you put it that way.
This theoretically could be a 2 to 1 mux.
Yeah, because I could have just this. I mean, I could have either one. Doesn't matter. I could have just this line coming in, and if either it's I could say, well, it's lit. If it's lit, if it's not lit, if it's not lit, then well, this one could also be not lit. You might say. See, there's 3 options. There's either this one's lit, this one's lit, or neither of them are lit. That's why he uses mux, because there's three options. Either it's here, or it's nowhere. But
if it's nowhere, it's going. It's.
But as long as I check over here what comes out of this OR, whether I have a hit or not, then I've already got that information. But you could do it this way. If it's nowhere, if it's zero, then what? You're saying, that's why I was saying that this line is really not connected. You see, because then if it's both zero, then nothing comes out here. That's the way it should be, if you can do it like this. But if you can do it the way it's written here, with they're all four connected, then you're going to have to check here anyway. And if you're going to have to check here anyway, because if they're both zero, you'll still get some data. You'll still get this, guys. So you'll have to know whether that data is relevant or not. So you have to check this. So if you're checking this, just have one line coming here and tell me, is the right one working? And if the right one's working, is the right one compounded, then send him out. And if it's not him, then send the other one out in every case. And then I'll have to just check if there was a hit or not. Yes, it could work. Could definitely work with them 2-to-1 mux.
Is there a reason to use the 4-to-1?
He may have copied the diagram from a different, he may have edited a previous diagram. I don't think there's any legit, I mean, I said there's a kind of a reason why, because if I would have done if I would have not connected this line, then I would have all the information here. You see what I mean? Then I would know. If I got nothing out of here, then it's a miss. I mean, of course, nothing is a bit confusing, because what does it mean, nothing? Nothing means all zeros, but all zeros could be the value in the data. Every data could be zero. So actually, you have to check the hit in any case. So yeah, it seems to be superfluous. It seems to be superfluous. But that's the way he drew it. Or maybe you just want to do it simple, you know.
And three
essentially what you're saying is chop off this line.
Also,
chop off that line. But of course, right? Chop off. If you'd have 4, you see, if you'd have 2 more, then what would you do then? You see, then you'd have to have a 4 anyway. You'd have to have 4 lines here anyway.
If it was a 4-way?
If there was a 4-way.
Is that a thing?
Yes. Remember we talked about it as n-way. You have any number as long as the power of 2. Yes, it's definitely a thing. You have a 4-way. That way, yes. You're expected to understand how a 4-way would work. It's just the same thing, except you'd have 4 of these. And the hit would have to check an OR of all 4. And here I would have 4 lines coming in instead of 2. Now, could I reduce it to 3? Probably, but there is no such thing as a 3 entrance. So you see, that's why he did it. He did it because he wanted to show you how you're going to do it in the future. In the future, if you'd have 2 more here, then you'd have to have 4 entrances here.
Okay, but an 8, you need an 8. Doesn't it just match the amount of ways that we have?
It matches the amount. It matches the amount of ways that you have. Exactly.
So why do we have a 4 now?
We don't. We have a 2 now.
Wait, what?
I'm talking about the S's. I'm talking about the S's, the selectors. The selectors are, I either select this one or that one. If I have another one, I gotta have another selector. If I have another one, I have another selector. When you have 2 selectors, by nature, you have 4 lines here. When you have 3 selectors, a multiplexer, that's the way it works. If I'm gonna have 4 lines here, I'm gonna have to have 16 selectors over there. 16 entries.
But a lot of those inputs aren't going to be anything. Like in this example, 0 and 3 will both not really be real.
Right. Yeah, maybe there's some other hardware you could come up with that would do it better. But it doesn't really matter as long as what there works. You know, that's what, for the exam, put it that way. For what you have to know is you have to know what will work and what will not work. This will work, and it would work with a bigger one. Then it would be certainly a waste. Okay. Yeah, we did this, no?
Yeah, we did that one.
We did this one.
We did?
Yeah, we did this.
And that.
And this is the same one.
And that.
Thank you. If you don't remember,
This I
This-
do not think we did.
exactly, this is new. So if you don't remember that we did this, you can look at the video from it's already posted for your convenience. Here we are, example 2. The case is like this. It's a read miss with replacement following the least recently used method. In other words, that's the algorithm. The least recently used is the replacement method. Replacement following the replacement method is, I could just write replacement method is the LRU. Replace the least recently used. And writing, let me move this, with the write back method. Which means what? Who can remind us what write back means?
Wait, what's the LRU?
Right back.
The LRU is least recently used method.
Right back is when we don't change anything in the actual memory. We just change it in the cache, and then when we want to copy it, when we actually want to copy it back, then we check the dirty bit, see if it has been changed. If it has been changed, then we copy it back.
Perfect, perfect. So we're using that system, and we're using the replacement, which means we're replacing the least recently used. We will now need a dirty bit for each block in cache. Well, that's because we have a WB. And here it is. D is dirty bit. We will use the write allocate method, which means if we want to write, we're going to put it in memory. Fine. Given the memory.
Back to that a second. Are you able to just quickly remind us? Right, allocate. Yeah.
We will use the write allocate method means that if we want to write to a particular byte, we don't just write to it in memory, we bring it into cache and then write to it in cache. In other words, we're going to write to it in cache. There was a theory to say, why not just, when you're writing, just write directly to the memory.
That is another option, isn't it?
Yes, that's called that's not the write allocate, that's the write no allocate method. Or the no write allocate method. I think they call it the no write allocate, which is stupid. It should be called the write no allocate. But, or the write don't allocate, better. Anyway, given memory is in the previous example, what does that mean? We've got a two-way system, like that. So it's not, memory is, I'm sorry, memory in the previous system, which means, did we have? Yes. The main memory is 256 bytes, and it's divided into 32 blocks. Because each block is 8 bytes long. Fine, so that's the same. The memory is still 256 blocks. That's what he means by saying, given given memory as in the previous example, we desire to read memory at address 232 base 10. Given that the cache before the read request contains data as in the table below, so let's see what's going to happen. This is the data. We have our set. This is the set number. I don't know why it's set number 0, 1, 2, 3. We want to read this one. What block is it in? Well, first of all, in other words, we want to see, is it in memory? Here is the memory. And it has an X over here, this means that there's no block here. When it says block 3, notice it's block 0, 1, 2, 3, 4, 5, 6, 7. We've got 8 blocks. Each one is 4 bytes. No, 8 bytes. 8 times 8 is 64. We have 64 bytes of cache. And we have 256 bytes of memory. We want to know is first of all, what block in memory is 232 in? Or what set is it in? We want to know what set is it in. We've got to divide it by 4 and see what the modulo is. Or we can just write the whole thing out in binary and see what it looks like. Here it is all written out in binary. So we know that 2 digits tells which set. And it's not these 2 digits, right? It's not these 3. Which 2 digits is it? Well, the set is 2 digits, but the offset remains the same as 3. The offset is still what it was, because we didn't change that. Remember, it was 8. So the offset is 3. So these 3 we ignore for now, but they're 0. And the next 2 is the set. So what set is it in? It's in set, well, it's in set 1, let's say. So that means it's in second row. It's in this row. It's got to be here or here. Now, according to this, I got tag 1 and I got tag 2 over here. Is that the right tag? Probably not. Probably not. I can just guess because the number 2 is a big number. And 232 is a big number. And I see that the tag has to be 7. Because if I take away the offset and take away the set, then I'm left with the tag. And it's 7, so it's not there. What is the block number? Well, it's 29. Fine. It's 29 because it's that and that. So first check if the block is resident. Now wait, I skipped a slide. Why did I skip a slide? Was there anything useful there? Let's check. Just so we understand what we're doing here. Everyone understood what I did here? This is pretty straightforward, I think. And we're given here the picture, and we see that in row 1, there is no 7. We actually see tag 7 over here. Could this be our block?
Because it's different, it comes from a different row.
Exactly. It's got a different modulo. It's a different row. It can't be ours. Okay. Just to keep. Now let's see what's written here. In the data column, I have written the block number of the cache, not which main memory block is currently residing there. Right. In the data column. Right. This is just block 1, 2, 3. These are just the cache blocks. This is going to tell us which block it is. For example, block 0 of the cache is in way 0, row 0, because that's where it is. Block 5 is in way 1, row 2. Let's see that. Block 5, here's block 5, is in row 1, way 1, not way 0. Fine. Just telling you how to read this diagram.
It's in row 2, but
What?
it's in row 2.
Sorry, row 2. Block 5 is in way 1, row 2. Let's see. You're right.
Which is the third row.
Which is here, 2, row 2. The third row. There's block 5 in the first way. Block 1 and 7, there is an X to indicate the data there is meaningless and valid as 0. Right, we said that. Assuming that the order of the, here's a key point though. Assume the order of the block's access is 0, 2, 3, 4, 5, 6. In other words, the order of the numbers is the order. Numbers indicate cache, wait a second, blocks. In other words, the one that's sitting in the cache in place 0 was the oldest one there. The most recent one we touched is 6. This means that the block 0 was the least recently used. So according to the least recently used algorithm, we should replace first block 0. I mean, given that the set is the same. Note that 1 and 7 are absent from the list because they have not been used at all. They're valid as 0.
So isn't 1 and 7 going to be used first? Aren't we going to first fill it up before we start replacing things?
Yeah. Not necessarily. Depends if that's set 1. Which one? We said 1 and 7. You're right. So you're right. 0 would not be the least recently used. Really, this would be first used instead of that. I was just trying to show you the idea of what recently used is. The oldest one. I'm just trying to say how to understand this order. All right, I can change it to be block 6 is the most recently used. But anyway, it's still true that 0 is the least recently used. Except the others weren't used at all. Okay, so we saw this. First, check if the block is resident. We saw that the block is not resident. Set equals 1, so we will check row 1 in both ways. Remember, the tag must be 7, but neither has this tag in row 1. So we need to bring a block. We need to bring block 29 from memory into the cache, and we will place block 2 in way 0, Which set we have to be? We have to be set 1. So we replace block 2 in way 0 since it is the older of the 2 blocks in that set. That's the concept. That's the concept of least reduced. Since the dirty bit is 1, we will need to write the block back to the main memory. So let's look at that. We're going to replace block 2 over here in row 1. The dirty bit is set. So that means we're going to have to copy it back. It's valid, so we can't just replace it. And the tag is 1. It's not going to be 1 anymore. It's going to be 7 when we put it in. We will calculate the write back address like this. Now we have to figure out where to write it back to, right? We're going to put 29 in here. That's very nice, but what about whatever's the information in block 2 has to be written somewhere, and its tag is 1, and we know that it's in set 1 also.
So we could figure out the
and
block.
We're going to write back all the block. Now, we don't have to care about the offset. We're just going to write back the whole block. Yeah?
The tag and the set together is the block.
Exactly. The tag and the set together is the block. So actually, we know that the block number is 101. No, it's 001, whatever. But it's 101, which means it's, what is that? 4, 5? 5, yeah? Let's see if we did that right.
And it's going to put the offset after, it's going to set it to zeros, since we're copying the whole
Now,
block.
we didn't store any offset. We have no idea what was written. We know that something was written in block 2, but we have no idea what. So therefore, we're going to write the entire block back to memory. So we don't care about the offset, because we don't have any record of which got changed and which didn't. We talked about that last time.
Right, so the offset's going to be all zeros?
What offset? No offset.
We
no
have
offset.
to fill it. Well, the address.
We are going to write a whole block.
Right, but I'm saying the address has to be more
It's
bytes.
not the address. There's many addresses. The starting address will be all zeros, yes. The starting offset will be all zeros. But then we're going to write the one that's all zeros, then we're going to write the one all ones, all twos, until we write all 8 bytes. But that's not asked. That's not. So, okay. We will calculate the write back address like this. The tag is 1. The tag is 1, which is equal to 001. And the set is 1, which is equal to 01. So therefore, the block number is 001015, just like I said. So we will write it back to main memory in location 5. And that's it. That's all you have to say. Obviously, it's going to start at the beginning of block 5 in memory. You can ask, where is block 5 in memory? Well, it's going to be location, I guess 4 times 8. That's the first byte of it. After this, we will bring block 29 from memory. In other words, first we have to write back. Then we can bring block 29 from memory into block 2 of the cache. We will set the dirty bit to 0 since we haven't written to it yet. And the tag field will be set to 7, not 1, what it was before. And now the CPU can read or write to byte 232. In this case, it wanted to read only. It will find it in the cache in way 0, row 1, offset 0. The current status of the cache. Now the cache looks like this. The dirty bit is 0 because we didn't write, we're just reading. And here it is 7, and the valid bit remains 1. Now the order of block access is no longer what it was. It's now we've accessed block 2 in the cache most recently. Now that's an interesting system, by the way. We could just keep an ordered list here. Actually, it's not so hard to keep track of the most recently used. We don't have to add a number every time. We just, every time we access something, I don't know, it's not good. It's not good. I was thinking every time we access something, we just stick it in here and push off the one from the end. But that's not good because we could have 2, 4, 2, 4. You know what I mean? And then it could have whatever, 2, 4, 5, 2, 4, 5. So as we push off, the 2 will go off when we move 2, but really 5 is older because 2 is over on both sides.
But why would 2 be on both sides? Or you're saying
If the access order was 2, 4, 2, 4, if it was 2, 4, 5, 2, 4, that was the access order. 2, 4, 5, 2, 4. Now if we push off the oldest one, what's listed on the left is not going to be the oldest one, because actually 5 is the oldest one, because we access 2 and 4 after 5, in addition to accessing before 5. We have to sort of also make sure that the numbers only appear once in the list, right? We can maintain a list of accesses where every number only appears only once, and where every time we access something, we put it on the right. So that means before, if it would be 2, 4, 5, it would be like, let's say 0, 3, let's say it was 2, 4, 5. And then we access 4 again. We wouldn't add a 4 here. We would take the 4. First, we would check if 4 already exists. And if it does, we'll move it over to here. If it doesn't, then we'll add it here. And we'll keep a certain size. So we could do it. But again, it's going to take, to do all that in hardware, you know, it's not, I don't know how to, I mean, you have to think about it, you have to plan it out. Clearly, the LRU access order will need to be stored in another memory location. No, that's what I'm just saying. We have to store this somewhere and manipulate it with some hardware. Okay, and that's all just to save us taking out the wrong one from here. But that could be actually very important. Because, right, otherwise we could keep taking the same one out when we wanted to keep using 1 and 2, 1 and 2, 1 and 2. It could be we never use this side guy because he's got somebody else in. We just by chance. Anyway, random is probably the best one. Example 3, write, miss, no allocate. So I have another combination. It's a write, miss. In other words, we're trying to write, but the thing is not in memory. And we're doing write without allocating. Well, that's easier. We don't have to use the cache at all, that means. And we're trying to do a write. So assume the cache looks as it did before. As it did before, example 2. The CPU wants to write to location 232. Since we are using the no write allocate method, the data will be written directly to the main memory and not to cache. As we saw in the previous example, 232 is block 29 in main memory. So the CPU will simply write to block 29 in main memory at offset 0. What if the data were in cache? Would anything be different? What if this were a read? Would there be anything different? That's the end of the chapter. What do you guys say?
Well, if it were in cache, we would probably write to the cache.
And
We'd write to the cache, and also we have to write to the memory, or depending on how we're writing.
Right. Actually, it's not said here. Depending on, it's not said in this question. We're not given whether it's write through or write back. But actually, we are kind of, because it says given. It says before example 2, we had no dirty bit. Assuming he meant like that. I don't know what I meant by before example 2. If we meant this diagram, then we know for sure that it's write back, in which case we would just write to the cache. But if the picture looks like this, then it's write through for sure, because no dirty bit. So the answer to this question is, would anything be different? Well, for sure, yes. Yes, then we were different, we would write to the cache, for sure. And if it's write through, we would also write to main memory. What if this were read? Would anything be different?
What do you mean by that?
We were trying to write and it wasn't in memory. Now we're trying to read and it's not in memory. We can do anything different? Or what's different?
You don't need to update the cache.
What? Your connection is not great. Maybe type.
Then
it.
you don't need to update the cache.
I don't hear you. You better, Eliezer, I can't hear you. You better type it.
He was saying that we don't need to update the cache, I'm pretty sure. I think.
In other words, we don't need to bring any, well, it's not in memory. We do need to update cache. No, the opposite. If this were a read, then even if it's a no, it's a read miss now. Even though it's no allocate, it's no write allocate. But there is a read allocate. So therefore, we would bring it up from memory. In this case, we would just write directly to main memory. But if this was a read miss, even though we're using the no write allocate, that doesn't say no allocate, it says no write allocate. Because no allocate would be completely senseless. Then we would never use the cache at all. It's only on write we don't allocate, but on read we would, yes, something would be definitely different. We would bring the whole thing up into cache, and then we would read from the cache.
There's no such thing as a no read allocate.
That is correct. That makes no sense.
So previously, the only reason you would have that for write is because we don't do it as often.
Yeah, and because writing is no indicator of future writing. That's the assumption. But reading is a predictor of future reading. All right, that's it for chapter 11. Let's start chapter 12. Yoo-hoo. Yay. Chapter 12 is also a biggie. Designing digital systems with algorithmic state machine charts, otherwise known as ASM charts. Now, you guys did these in digital systems?
Have to see one.
I think, here, I'll show you one. Because actually, I want you guys to, this. You did stuff like that?
Yeah, it looks, yeah.
All right, good. So we'll look at those. Yep, take out your notes from your other class. All right, our motivation. So this is actually referring to the other class. Insert, view, present. In the digital systems course, we learned methods of planning and realization of sequential synchronous systems. Okay, sequential, that's the key point. In other words, remember, that's different from just logic gates where the data just comes and boom, I got everything at once. Sequential means that not everything at once, but we want to actually, remember I said to let's say, move the things around in the keeping track of least recently used data requires searching and then moving things around. It requires a certain order. That would be sequential. That would be the realization of a sequential synchronous system. Sounds very fancy, but really just means that the hardware does things in stages as opposed by time pulses, as opposed to just writing a logic gate and boom, everything comes out. This method of the methods of planning and implementation were based on the use of flip-flops and basic logic gates. Right? I guess we use the flip-flops to store the data. There are two main drawbacks of these planning methods. The state diagram that describes the operation of a serial system is not sufficiently clear to easily understand the operation of the system. Okay, saying the state diagrams are not so clear. In the implementations, we use flip-flops. In basic cases, did not use complex integrated circuits such as counters, memory shift registers, etc. In other words, it's too basic. Too basic and too unclear. All right. Take it or leave it. That's the statement. Advantage of using integrated circuits to solve the problem of planning and realization of serial systems. Realization using complex integrated circuits simplifies the design and allows us to save components. You guys did the digital system course a lot more recently than I did, so maybe this will remind you of something. In the digital system course, we made various designs for a series detector. Did you do that?
Yeah.
No, to detect, what does it mean, a series detector?
Detect a specific series of numbers of ones and zeros.
Mm-hmm. These designs required a number of stages in planning. Did you make a state diagram, a state table for those?
Yeah.
Okay, good. You should show me after class. We will see. Actually, seriously, if somebody has their notes, they can photo them and email to me. I want to see what he's talking about. We will see that using an integrated circuit simplifies the design and implementation of the series detector. So we'll do it in a better way. Problem description. You want to realize a 101 series detector with overlapping. And you want to detect 101, such that with one clock cycle, one bit enters the system. So in other words, we're going to get a 1, then a 0, then a 1, then a 1, then a 1, and then a 0 and a 1. We want to know whenever we got a 1, 0, a 1, followed by a 0, followed by a 1. We will use a register shift, which has a serial input and a parallel output. Let's see it. Shift register with a serial input and a parallel output. Here is the parallel output. 3 things coming out. Notice, here is our Galai 101. In other words, this is a detector. This is a 101 detector.
That what? It sees if those numbers are 101.
Yes. Well, yes. Although I see here it's inverted. I guess essentially what it does is if it's all 1, it looks like it's just a big and. If this is a 0, then this will be a 1, right? And that'll be 1, 1, 1. So if it gets 3 1s, it'll be true. So there's a big and. That's a D for detector. So that is our implementation. This is a big and. Fine. But we have to have this not here. I suppose you did something more complicated in digital systems?
Yeah.
Okay, yeah. So now we have the Shalom, the clock coming in. Sorry, this is in Hebrew, but good to see a little Hebrew. Sha'on is the clock cycle. C is clock. And we have Knesat Tori. This is a serial input. That's what the S stands for. Serial. You don't even need the Hebrew here. The S tells you serial. The C tells you clock. And this does. I don't know if you ever saw such a thing. It's a shift register. You ever hear of that?
It shifts everything over and adds 0 at the beginning or the end, depending if it's a left or right shift.
Something like that. It doesn't actually add 0, but it just shifts. It stores the first data comes in and it goes into Q0. The next clock cycle, whatever was in Q0 goes to Q1, and the new data that comes in goes to here. The next clock cycle, it goes to here. What was in Q1 goes to Q2. What was in Q0 goes to Q1, and the new one goes to Q0. The next clock cycle, again, what was in Q2 goes to Q3, until eventually what was in Q3 gets discarded. So it's storing. That's why it's called a shift register, because it's a register. When you hear the word register, think storing. Stores the data, but it also shifts the data. So it's a shift register. So if I got a 1, 0, 1, and as it starts off, it'll just be a 1 here, and this will be not true. Then it'll be a 1 here and a 0 here. It'll be not true. Then it'll be a 1 here, a 0 here, and if it's a 1 here, it'll all of a sudden be true. Then if it goes off, it's a 0 here and a 1 here, it'll for sure not be true, whatever this is. But then it'll be true the next clock cycle when this is a 1 and this is a 0 and now this has become a 1, let's say. So this will detect my 101. Now we're just explaining it.
How would you do this without overlap? You couldn't use the same thing?
Without overlapping? In other words, this will count the same one twice. If it's 1, 0, 1, 0, 1, then it's 1, 0, 1, and then we shift it, we shift it twice, this becomes 1, 0, 1, and we're using that 1 again. So we're double counting that 1. You're asking, how could I do it without double counting the 1?
Could we could connect the AND gate? Can you hear me?
Yeah.
We can connect the AND gate to the clear.
Uh-huh. So the minute he got a positive response, he'll clear everything, and then he'll start again. That would be excellent idea. Excellent idea. Problem is that this has got a roof on it, and this has got a roof on it. We may have to connect we have to think about it. We may have to connect the opposite. We have to put a knot here, but we'll see. We're about to describe what the clear does, but it may be on, maybe on low that it clears, or maybe on high that it clears. So either we connect it directly or with a knot. Let's see. The beginning of the operation, clear equals 0, causes the register reset. So it needs to be 0. So we're going to have a knot. But it's not going to be a knot. It'll be a 1. Now, GOG, if we put a 1, it's a little bit confusing. Clear 0 has to be, what do we call it in Hebrew? GOG. How do you call it? Overline? I don't know. What do you call that in Hebrew? In English, when you have a inverted. Clear inverted has to be 0, which means that if we if clear is 1, everything will be good. It'll clear it. So this will just go directly to clear, as long as clear inverted is that. Depends how it's not enough to look at this picture and to know what it means. But if clear inverted equals 0, then the register is reset. I.e., in the initial state, all register values are Q being they're all 0. But inverted clear equals 1 causes the register to switch to shifting mode. In other words, as long as you keep it in clear mode, it's no point in shifting. On each clock pulse, 1 bit is inserted into the shift register. When 101, 3 consecutive clock cycles appears from the input X, then D becomes 1. Note the simplicity of the solution compared with the solution using flip-flops and gates that we learned in the digital systems course. Well, it's simple because we just imagine that we have this shift register. Isn't that right? You guys did the same thing, but you did it without a shift register. You essentially built a shift register. Does that ring a bell?
Yeah, we use flip-flops and stuff.
Right. Well, that's how a register works. Uses flip-flops. Fine. That was just an example. Okay. I mean, I don't know what the point of this example is really, because we're just saying, you have to think about it, but we're just saying that we can get the same results now with our new capabilities of just imagining things. Imagine we have this shift register, then yes, everything is simple. An algorithmic state machine, an ASM. By the way, I recommend you can look up on the internet what this is. You can. You don't have to rely only on the material of the course. Is a system that performs, and you don't have to rely on only my information. An algorithmic state machine, and that's true, by the way, in your entire college career. You're not limited to the material that we present you. An algorithmic state machine is a system that performs a finite number of operations according to predetermined conditions. Conditions also include external input to the system. In other words, if this input comes in, the state machine does this if it's in a certain state. That's the idea. That's what a state machine means. It means that when I'm in state 1 and I get that symbol, then I do this. But if I get that same symbol and I'm in state 2, then I might do something completely different. So that means I have to keep track of my own state. In fact, that is how, well, we'll get to it. But this is eventually going to be how the controller works. In other words, ASM is a system that performs an algorithm. The system is a serial system, right? In other words, pulse comes in, pulse comes in, pulse comes in, then I decide what to do. Design of a serial, and I design each pulse, I can decide a new thing to do. Design of a serial system using the method we have learned in the digital systems course will be very complex for a system with large number of states. So the solution is to separate each digital system or ASM system into two units. And we call it the controller and the data processor. Processor is also called the data path. Well, he's just explaining now what you kind of already have seen. When you have a computer, when you have the MIPS, we had a controller and a data processor. We would call the MIPS. Data processor, what's a data processor? Everything that's not the controller. The stuff that processes the data. The add goes through here and goes that. And notice there were states in that thing. Because if I'm in other words, if I'm in state one, I'm in stage one of the execution, I do certain things on the control lines. And if in stage two, I do different things. So the state affects what I do. And if I'm in stage three, I already have to check the command, the instruction. And then I'll do something based on that. And then I can go to also different states. I may have several states. I may have like 8 or 9 states in the MIPS. And then I do different things. If we recall the MIPS processor, we have studied extensively in the previous chapters. The main controller that appears in the diagram is the controller, and the rest of the system is data processor. Note, when we studied the MIPS processor, we dealt mainly with understanding the data. I can't see it, but the data path, and treated the controller as a black box. Note, the inner parts within the dotted line is the interior of the system, and the part outside the dotted line is the outside world. So here you go. Here is your MIPS. You've got some clock that comes in. You've got a data path. That's all the the ALU and all the all the different things that are there. The register file, and then here you have the controller, and the controller has inputs and outputs, but it also has outputs to the data path. It tells the data what to do, and it also has status coming in from the data path, telling it, I am now on this state. I am now in this state. In other words, there's some information that goes into the controller from the data path. For example, certainly the most basic thing that it's going to get. Can anyone tell me what's the most basic data that the data path will provide to the controller in MIPS?
Dirty bit?
What?
Something like a dirty bit? Something like that?
No. Go back to thinking of MIPS. Forget about dirty bits. Think of MIPS that you learned. What line goes into the controller?
The opcode?
Yes, the opcode. Most basic signal that goes into the data path, it's like a status kind of, is the opcode. All right, but certainly it could give other things. It could say that, also the clock tells it. The opcode goes in, and then the clock tells it I'm in state 1 or state 2. There are other things that could theoretically go into the controller. Okay, explanation. The controller is a serial system with external inputs and outputs. We didn't really see that in our course so far. But we did see control signals for the data processor and status signals from the data processor. Example of an external control entry. So we're asking, right? We didn't see what are external inputs and outputs for the controller. Well, start. Turn on the computer, I guess. I don't know. Some kind of start. Example of an external control, ready. He finished. He's ready to do something else. Again, we're not talking necessarily about our computer. It could be another computer that works in a different way somehow. But the point is, it could say that it's finished. Signal, in other words, we could have some computer that does a whole lot of computations, takes it hours, and it's all by hardware. And at the end, it tells me ready so that I can start a new computation. So we could have an external system. Think of 1967, Star Trek. you know, you ask the computer to do something and it tells you ready when it's finished. Signal indicating the end of the system operation and the readiness of the system to start a new operation. The controller actually implements a state diagram and its outputs, which are the control signals that go to the data processor, and external, that's its output. Fine. So we're going to see how to make a state diagram. The inputs to the controller from the data processor and from the outside world are state signals that determine the transition from state to state. In other words, the clock cycle is going to tell me go to the next state. And what previous state, the combination of what previous state I was in, what the clock signal is, and what signals I got for the data path. Those three things together will tell me to go to the new state and what that new state will be. If we think about what the controller does, we realize that it is state dependent, right? In MIPS, if you just think about what it does, if it's in the third stage of the operation, it does something different than it's in the fourth stage. So it has to know what to output now. It has to know what stage it was last in. The controller has output lines whose values change depending on the state or step of the procedure it is in. Therefore, using state diagrams to describe it is very natural. All right, we'll stop here.
Thank you.
Sure, thank you guys.
Are we gonna have like a class that is kind of going like kind of doing practice questions for the exam and things like that?